Good morning, everyone. I am Lloyd together with
Dexter, Sestoso,
and we are tasked to discuss the ion exchange, which we are going to focus on cation exchange capacity and anion exchange capacity. What is ion exchange?
Ion exchange in soil is a reversible chemical reaction which involves interchange of equivalent amount of ions between two phases in equilibrium in contact. And also, the exchange of ion is important to plant nutrient availability and retention in soil.
Furthermore, the exposed surface of colloidal clays and humus are commonly portrayed as an electrical double layer, where the inner layer effectively is a polyvalent anion and the outer layer consists of a warm or cloud of cations around the clay and humus particles. When any ion is adsorbed from the soil solution, an equivalent amount of another ion in a double layer is released into the soil solution. In order for us to understand what is cation exchange capacity and an ion exchange capacity, we will revisit first basic chemistry. So, everything is made out of atoms. Atoms is the basic unit of life. The atom is composed of protons inside the nucleus, which is a positive charge, while electrons is a negative charge that surround the nucleus.
Atoms can gain and lose electrons. If the elements lose electrons, it will result to a positively charged that is known as cation.
And if the element gain a higher electron than protons, it will result to negatively charged that is known as an ion. Now, we will discuss the two types of ions, but first, we will start on cation. This positively charged cation can be divided into two categories: the acid or acidic forming cations and basic or alkaline forming cations. The cations that are mainly concerned in soil are the calcium, magnesium, potassium, and sodium. They are all alkaline or basic cations that is used by plants as nutrients. While the acidic or acid-forming cations are hydrogen, aluminum, and ammonium that surrounds the nutrient cations to get closer to the negatively charged exchange site. So now we know what cation is. How about cation exchange capacity and anion exchange capacity? Soil particles have negatively charged and positively charged sites that attract and hold positively charged cations. Cations exchange capacity is the measure of how many negatively charged sites are available in your soil, while the anion exchange capacity is the reverse charged sites that are available in the soil.
The exchange basically works like this. Plants, roots, and soil microorganisms give up positively charged hydrogen ions. If these hydrogen ions can surround the nutrients or basic cations and get closer to the negatively charged exchange site, the hydrogen ions will fill the exchange site and neutralize the charge.
This means that there should be equal number of mole equivalents of the replacing cations and the cations to be replaced. This is the rule that is followed in the cations exchange reactions, or what we call as stoichiometry. Since I have mentioned stoichiometry, which is known as the process of cations exchange reaction, and for you to know more about it, I will present to you its characteristics, such as reversibility because it possesses an equilibrium reaction, speed since it involves extremely rapid counter-reactions, and extent because it only depends on the amount provided by the principal factor, which includes concentration of the replacing cations, relative replacing power of cations, and relative adsorbability of cations. This frees the nutrient cation of its static bond and it can be taken up by a plant. There are following factors that affect the cation exchange capacity, which includes soil texture, organic matter, management practices, temperature, and moisture. Soil texture, since Soil with a higher clay content generally has a higher CEC because clay particles have a greater surface area and more negatively charged sites for cation exchange capacity. Organic matter because soil with rich in organic matter tends to have higher CEC or cation exchange capacity because organic matter contains functional groups such as carbolex and hydrolex groups that can hold cations. Management practices such as adding organic amendment, maintaining proper soil pH, and avoiding excessive tillage can positively impact cation exchange capacity. The last one is temperature and moisture. These factors can indirectly influence CEC by affecting microbial activity, organic matter decomposition rates, and mineral weathering processes, which in turn impact soil properties related to CEC.
With a higher CEC, we will meet the following significance of cation exchange capacity, such as nutrient retention, buffering capacity, water retention, soil fertility, and environmental protections.
With those significance, it provides us the importance of cations exchange capacity in the soil. So, how do we measure CEC or cations exchange capacity? Using the steps and formula provided, we can now trace the level of CEC in the soil. The formula is CEC is equal to summing the number of mole equivalent of cations per 100 grams of soil. But before we can come up with this formula, there are following steps for us to determine the following cations value. Step 1. Determine the gram equivalent weight of each base cation. Each base cation has an atomic weight and valent number in the periodic table of elements. For example, the atomic weight of calcium is 40 grams per mole and the charge is 2. We divided each atomic weight by the charge to calculate the gram equivalent weight, which is 20. The value of each base cations is outlined in the example that we provided.
After we solve the equivalent weight of each ions, we will now proceed to the step 2, which is to convert the weight of equivalent of each ions to milliequivalent weight. The formula used to convert the equivalent into milliequivalent is equivalent weight divided by 100, which is the magnitude of each negative charge. Then now, we will get the number of milliequivalent of cations, and for us to solve the cations, we will divide the weight of cations given or percent by the weight of 1 milliequivalent of cation.
And now, we will solve the value of CEC by summing the number of milliequivalent of cations per 100 grams of soil. Since we now have the CEC, we can now also solve for the percent of base saturation by dividing the number of milliequivalent bases to the CEC and multiply the quotient by 100. And also, there is another way to calculate the percent of base saturation, which is to subtract the number of milliequivalent of acidic cations to the CEC, then divide the difference to CEC and multiply the quotient by 100. Moreover, to get the number of kilogram of cation per hectare, we simply multiply the milliequivalent cations to equivalent weight of cations, then multiply by 20. And lastly, to determine the parts per million or ppm, the kilogram weight of elements per hectare is simply divided into 2.
So now, we know how to solve CEC and AEC, and it's important to the soil. And with that, we are very thankful for the short time that you lean in watching the video. Thank you!